record. So what I thought we would do today is work through some problems where we look at, so we'll take a quick look at some distributions that you guys are studying. That I hope none of them are new to you. I do want to talk a little bit about grading and Project 1 briefly, and then we'll just look at these 5 distributions: binomial, hypergeometric. Geometric is a special case of negative binomial, so we'll look at those, and then the Poisson distribution. And the primary goal tonight is to be able to understand what we look for determining which one to use. And so we'll take a look at some exam problems that I've given in the past, and we'll focus our efforts on identifying the correct distribution, and then we'll work with it to answer the questions. So let me just first state just a few things about grading. I'm well behind. I know I'm well behind, but I'm about 2/3 of the way through the first problem set. No, I'll have those grades posted, I hope, by the end of the day tomorrow, if not Saturday for sure. I did grade your group Project 1, so those are graded. Those looked really good. I was originally going to spend 20 minutes tonight going through how I would have done it, but you guys, you've already nailed it, so I don't think that's worth our time. If you do want to go over something from it, let me know, and I'd be happy to spend some time outside of Meetup doing that with individuals or groups. But you guys both groups did an excellent job, and I might have done things slightly differently, but I'm not sure it would have been better. So, in fact, the group that came up with the coupon idea was, that's even above and beyond. So those looked really good, and I think the grades reflected that. So, and then I'll, once I grade problem set 1, I'll get set 2 graded. I do also. Let me just go in here. So I did post on Monday. I posted the next module, so you can start working through this. There's a little bit more from Chapter 4 that we cover, and then we cover Chapter 5 is just what we're talking about tonight with the different distributions. And this one has an individual assignment. So Module 4 will have a group assignment, and they'll alternate from there. And I'm going to try and release 1 a week going forward, if not earlier. I'll try and release them early as they're done. As I think I've now figured out the right level for you guys. And then what I'll also be doing tonight and tomorrow is, you got these practice sections. I know yours looks a little different from mine, but you've got these practice problems I ask you to do. I'll post my solutions, and then I'll post resources as well. So if you've got a specific question you don't know how to do, or you're trying to figure out, if it's a practice question, have at it in the discussion forum. So I created a discussion board for week 3, or module 3, excuse me. Have at it there. Say I'm looking at problem 4.16, trying to figure it out. This is what I've tried. That'll work best if everybody's there and participating. So, have at that. You can ask me as well. I'm trying to figure out why it shows those as not read. I've read those. But anyways, so make good use of this. I'm also going to post, Sharad suggested that I post some extra problems that you guys can work on in the discussion forums. So I'll do that as well. And again, you can create a thread for each one that you guys want to work on together and discuss. I'm hoping that we can make these things pretty simple by the end of the night tonight, so that identifying correct distributions is not a challenge that you face too much. Both groups looked at the Poisson distribution for the sandwich problem, and when I generated the data, that is in fact the distribution that I used. So that's a good catch. And then, where you took it from there, the groups did a little bit different things, each group, but they were both pretty good. Okay, any questions before we move on? All right, so what I'm going to do is a quick walkthrough of the 4 distributions, 5 distributions, and their properties, and what we look for when we're trying to identify the right distribution for a scenario. And then I'll just, like I said, I'll pull up some practice problems that we can do together, and we'll talk about, first off, how do we identify the correct distribution. And I think by the end of this hour, that should be comfortable. I think for most problems at least. You can always throw tricky ones there, but for the basics, I think you'll be comfortable identifying the right distribution. So the big one from Chapter 4 is the binomial distribution. And we talked about this one last time, so I'll just briefly mention. Again, it's a situation where you've got a fixed number of events or a fixed number of trials. So if you're flipping a coin 10 times, that's a fixed number of trials, right? 10 flips. In real life, we often will use the binomial distribution for well, all sorts of things. So whether you'll have a boy or a girl for your child is modeled with binomial typically. What color a plant will be is one of the earliest uses in genetics with Mendel. You can model that stuff with all sorts of neat different approaches, but the binomial distribution is one way to do that. So in genetics, it's pretty popular. You name it, you can probably come up with an application of this. One of the problems I give my students in Introstats looks at the binomial distribution for failure of O-rings with space shuttles. And then their job is to calculate the probability of O-ring failure at different temperatures. And those probabilities change based on the temperature. And that's all based on the Challenger explosion back in the 80s, which I actually saw on TV. It was traumatic. I was homesick from school and I saw it on TV. And so for binomial, each trial is independent. There's a fixed number of them. There's a clear success and failure, although again, success could be, yep, you got the disease. How great for you. So that's arbitrary which one is labeled success and which is failure. And the probability on each trial is the same. Hypergeometric then is similar in that there are a fixed number of trials and there is a clearly defined success and failure. And again, it's arbitrary. But the differences here are in the other two properties. So with hypergeometric, we're sampling without replacement. So you can imagine if you have a box of chocolates and half of them have walnuts and half of them don't. Once you pick a chocolate, the probability of the next one having a walnut changes depending on whether you drew one with a walnut or not. Right? So if you had 5 and 5 and you drew one with a walnut, now there are only 4 remaining out of 9 with a walnut. So the probability on the second trial is different. It's not the same throughout. And that's because the trials are not independent. The probability on the next trial depends on what you picked in the first one. So the hypergeometric is the case where we're sampling without replacement. Binomial is often referred to as sampling with replacement because the probability doesn't change. So that would be the case where you pick the chocolate and then you put it back and then you pick again. Right? Or you pick one out of each box for 20 boxes. That's cases where the probability would remain the same. So the difference between binomial and hypergeometric is subtle, but that's what it really comes down to, is with hypergeometric, that's where you don't have the replacement, where the probability changes each time. The negative binomial distribution and in particular the geometric distribution, which the book focuses on, instead of fixing the number of trials, what we do is we fix the number of successes. And so, for instance, if you're interviewing job candidates, you might say, we're going to interview enough candidates until we fill 3 positions. And so each candidate you interview might have a 20% chance of meeting your requirements, and so you'd keep going until you find 3. So instead of fixing the number of trials, we fix the number of successes. And again, it has to have a clearly defined success and failure. The probability of success has to be independent and identical on each trial. So if the first person you interview is not sufficiently qualified, that doesn't affect the chances of the next person. In the real world, it depends on the scenario. That might not quite hold up, especially when you get people coming in pairs or in other situations where in sports, for instance, you get in a streak. So if you win one game, it might build some momentum. The World Series is underway, right? The playoffs are underway. So you might see teams that get streaky, hitters that get streaky. But in general, we say the probability is the same for each trial, and they're all independent. Geometric is negative binomial, where the number of successes is just 1. So negative binomial, you could say I want 5 successes or 20 successes. Geometric is just the special case where it's equal to 1. And we'll take a look in R in a minute, too, at the distributions. We'll plot some of these things to get a feel for what's going on. And then the last one is a little bit weird, the Poisson distribution. We don't talk in terms of number of trials. We do talk in terms of successes. But what we do here, and I think you guys are all familiar, what we really do is we talk about trials, but we talk about them in terms of tiny time spaces. So for customers coming into a store, for instance, we might say, each 1 second period has the same probability of a customer coming in. So we can find this really small time space that we say, in that time space, either there will be a success or a failure. But we don't treat it like a binomial, and we typically, the time spaces are so small that it's not practical to treat this as a binomial. So we use a different approach. This is also commonly used for problems like radioactive decay, traffic accidents, things like that. So we'll see some examples of this in just a minute. So let me switch to a Word document, and I'll record these as we go so that I can post them when we're done. And interrupt if you have questions. So let me change the font to be a little bit bigger. So let me, what I'll do is I'll copy over a problem one at a time, and we'll just talk about what distribution it might be. So here is, and these are all exam problems I've given in the past, so you get a sense of the kinds of questions you can do here. They're all pretty basic. So you've got a particular type of rose that will bloom in the first year after it's planted 80% of the time. And if a woman purchases and plants 20 Montezuma roses, we've got a number of questions we might ask here. So what's the probability that exactly 14 bloom in the first year? How many would you expect to bloom in the first year? And what's the probability that more than 18 will bloom in the first year? So if we go back to those requirements that I posted for each of the distributions, which one does this seem to fit? And what I'll suggest we do here is, let me see if I can fit both on one screen. I've got that flow chart that I posted. Let me pull that up because it walks us through questions about those different properties. So here it is. The first question I always ask myself is, are the number of trials that can occur fixed? And so let's ask that for this problem. Is the number of trials fixed?
Yes.
Yes. There are 20 roses planted, and we're going to see how many of them bloom. So the number of trials is fixed, so we say yes, and we move over here. Is each trial independent with identical probability?
Yes.
As far as we can tell, yes. I mean, you could get into things like, well, what about the soil? What about the, what if one plant is too close to another? But as far as we know from everything we're given, there's nothing like that going on. So we'd say yes, the trials are independent with identical probability. The number of trials is fixed. There's clearly a success failure here, right? Bloom or not bloom. So this is a binomial problem. And then once we know that, we can use our formulas for the binomial distribution to calculate these things. If you're curious, this thing here, this Binom PDF, that's for a graphing calculator. I use this formula sheet for my intro classes, and that's the syntax for the graphing calculator. But the formulas above that, these three formulas, the first one is the probability for any given number of successes. So for the first question, what's the probability exactly 14 of the roses bloom? We would plug 14 in for K for the number of successes, 20 in for trials, and we could calculate that. In this class, of course, we'd probably use R. It's pretty easy to do in R, and we'll look at that in just a minute. The second one answers what's our expected value. It's just number of trials times the probability of success. So on average, it would be 16 roses that would bloom, right? 80% of 20 is 16. But then when we say what's the typical number that will bloom, we typically say we want within a couple of standard deviations in each direction. And so we have the formula here for the standard deviation as well. And I believe, let's see, so 20 times 80% is 16 times 20% is 3.2 would be the standard deviation. Or excuse me, would be the variance, and then we take the square root of that for the standard deviation. I don't know off the top of my head what the square root of 3.2 is, but it's going to be, well, I don't know, about 1.7, somewhere in there. So we would then say 16 plus or minus 2 of the 1.7s. And so we would say it's probably going to be typically between something like 13 and 19 roses that would bloom each year. So the book walks through some of these different things, but the key here for tonight is we can identify which distribution it is, and then we would know how to answer these different questions. The probability that more than 18 of the roses bloom, we would calculate the probability for 19 and for 20 and add them together. right? Okay, that's one. Let's take a look at another question here. Let me copy it over. That didn't do what I wanted. Okay. So here we're going to talk about the daily arrival of ships in a certain port is reasonably independent. On average, about 4 ships arrive in a single day. So what distribution do we think is going to work for this one?
Poisson?
Yeah, so is the number of trials fixed? No, you could have any number of ships arrive. Is the total number of successes fixed? No, you can have any number of ships arrive. So Poisson doesn't, fit cleanly into any of the other models, and this problem doesn't either. So we would reach for the Poisson distribution. And so if you want to know the calculated probability, exactly 3 ships arrive, we would use the Poisson formula. The expected number is just lambda, which is the average, and in this case we're told the average is 4. So we would expect 4 on average, and then the standard deviation is the square root of 4, which is 2. So we would say 4 plus or minus 4. So on a typical day we would expect between 0 and 8 ships to arrive. Anyway, again, the emphasis tonight is really just on identifying which distribution these problems fit. Let's see, let me find another one here. Okay. All right. Okay, so a salesman sets himself a daily goal of making 3 sales. Because of his scheduling constraints, he's only able to make 25 calls in a day. So if you assume that the outcome of each call is independent, that for each call he has a 15% chance of making a sale, and that he stops after making his 3rd sale each day, now we can answer these questions. What's the probability that he makes his 3rd sale on his 18th call? So what distribution is that going to be? Let's see, so it looks like Rohan has said negative binomial, and I would agree with that. And the reason for that is as long as we steer clear of 25 calls, which we haven't said anything about in the first question, the number of trials isn't fixed, right? He could make his 3 sales in the first 3 calls, or it could take him 8 or 20, or he's going to stop at 25. But because the number of trials is not fixed, we go over to the right, and then we say, is there more than 1 success? Well, yeah, he wants 3 successes. So because it's more than 1, we say negative binomial. So what's the probability he does that on his 18th call? Under negative binomial in the formula sheet here, we can calculate that probability. What's the expected number of calls for him to have to make in order to reach his goal? Well, he wants 3 successes. The probability of success is 15%. So what we would do is say 3 divided by 0.15. And so we would expect him to take 20 calls to make 3 sales. And that should make sense to us, right? If he makes 20 calls and we expect him to succeed 15% of the time, 15% of 20 is 3. So this is just sort of capturing what we would intuitively think. I don't have the standard deviation formula on there for negative binomial, and we'll talk more. Well, I'll talk about it now. The reason for that is that the distribution, if you plot it for negative binomial and for geometric, they're very skewed. They're very right-tailed. They start at 0 and then they go from there. But because they're skewed, the standard deviation is not a useful measure for talking about typical values. So it's dangerous, in fact, to use them. You can calculate it, but it's not a useful measure. Now, let's move on to the next question, part C. What is the probability that he does not make his daily goal on a particular day? Now, how would you answer that? Is that still a negative binomial type of question?
I would say no because the number of trials would be fixed now at 25.
Right, so you're asking what's the probability he doesn't get 3 successes out of those 25. So now we have a fixed number of trials. The probability of success is consistent through each trial. And the trials are independent, so now we have a binomial again. So once we cap it at 25, we say, what's the probability of 2 or fewer using the binomial distribution? Yeah.
So that's actually confusing to me, that for the same situation, we can use 2 different distributions to come up with answers to different questions.
Right, and the reason for that is because for parts A and B, we're not capping it at an upper level of calls. We do, implicitly, we have that 25 there in the back of our minds, but when we say what's the probability that his third sale occurs on the 18th call, the number of trials is just not fixed there because it could occur on the 17th or the 15th or whatever. And so that question needs to be answered within the framework of we don't know how many trials. And so we would reach for negative binomial. Part C, we do know that there is an upper limit of 25. So he made 25 calls and he got fewer than 3 successes. So now what's changing is the number of successes rather than the number of trials. That's fixed. So yeah, it is a little bit confusing. All 5 distributions are interrelated, right? They're all about successes and failures. Poisson's a little bit different in that the failures are just, nobody comes in kind of a thing. But even there, these are all in terms of successes and failures. And the question is just what are we capping and fixing and what are we leaving variable? So for questions A and B here, the number of calls is what's variable. And for question C, the number of successes is what's variable. Calls is fixed at 25. So you have to ask what question am I asking and trying to answer in order to determine the right distribution. Now, yeah,
right, I guess my thinking was for any given problem, there's a distribution for that problem. Versus in this case, well, I guess A, B, and C are different problems.
That's right. I was going to say you got 3 problems here. So, the question you're asking determines which distribution to reach for.
Okay.
The most common confusions will be what we just did here, where we switched from negative binomial to binomial, and the other most common confusion is not knowing whether to use binomial or hypergeometric. So we'll let me see if I can find one there. Here we go. Okay. Sorry, this is a little clunky trying to move back and forth between screens. Oh, wow, don't do that. Okay, I don't know why it's doing that. Let me make that a little bigger. We'll scroll down here. Okay, so you got a community with 42% Republicans, 51% Democrats, 7% Independents, and you're going to pick a panel of 12 community members to participate in the discussion. Now, this is a case where if we're doing hypergeometric, and you might think hypergeometric here, right? Because once I pick somebody, the probabilities change, right? If I have 100 people in my community and I pick one of them, now I've only got 99 left to pick from and the probabilities change. So this is a question where it's a little bit tricky. We got to figure out which distribution to use. And the answer is still going to be binomial, and the reason for that is we don't know how many people there are. And if you look at the hypergeometric formulas, we have to know the population size. Right? There it is. And we don't know the population size here. All we know are the percentages. So we're going to have to treat this as a binomial case. And for each question, we have a different definition of success. Right? So for question A, we're saying what's the probability of 4 Republicans? So we would say Republican success with probability of 0.42. Failure has a probability of 0.58. We would add the other two together. And then what's more likely, 5 Republicans or 6? It's still, you'd use the binomial distribution to calculate each of those probabilities and just see which one's bigger. And then down here we say how many independents would you expect on the committee? Again, we would say 7% is our probability of success for independence, 12 trials. So we would expect maybe 1, right? 0.96 independence is our expected number. So this is binomial, although if we follow our flowchart, we could easily select hypergeometric, but we can't use it because we just don't know those population sizes. So that's another place where it's often tricky. And the other thing that makes that even more confusing sometimes, if the sample size is less than 1/10 of the population size, you can use binomial even if hypergeometric is strictly correct. And the reason for that just comes from the correction factor here in the formula, where big N is so much bigger than little n that when you do n minus little n divided by n minus 1, that number is so close to 1 that it doesn't really alter the answer for the standard deviation. So that's where the 10% comes from, if it's less than 1/10 of the population size. So this is the other area of confusion. Should I use binomial or should I use hypergeometric? Just keep in mind, hypergeometric is fine if you know the population size, and we don't here. Let me find one where we do. Okay, here we go. Okay, so here we have a wildlife preserve. A sample of 100 deer are caught and tagged and released back into the preserve. And later on we take a sample of 20. And so what's the probability that exactly 5 of the 20 deer are tagged? So this is a case now where once you pick the first deer in that sample, you're not going to pick it again, presumably, right? You collect the sample of 20 deer and then you release them when you're done. And or perhaps a better way to put it would be you'd have to clarify. Do you catch one, note whether it's tagged, and then release it again, and then go catch the next one, or do you catch all 20 before you release any of them back? So if we assume that you catch all 20, this would be a hypergeometric, right? Because the number of trials is fixed at 20, but once you pick one, the probabilities change. But, again, 20 is less than 10% of 500, so you could use binomial here and you'd get roughly the same answer. It'll be slightly different, but probably not different enough for most purposes. With computing power what it is today, I would prefer just to use hypergeometric. There's no reason not to. But of course, computing some of those formulas before we had that kind of computing power was not easy. And binomial provided a nice way to get simplified calculations. So does that make sense, the difference between the binomial and hypergeometric, and why this one is probably better as hypergeometric? Are there any questions on that? Okay. So those are some simple examples. Let's switch over to RStudio for a bit. And what I want to do here is just show what these distributions look like. I mean, you guys can do this as well, but it's always good to visualize what these distributions look like. So let's take that deer problem. So let's say that we're going to do. So I'll create a vector from 0 to 20. So we're going to go out and we're going to sample 20 deer, and the probability is, it was 100 out of 500. So that's 20% for each deer. And let's take a look at the differences here now. So if you're curious how to use all these distributions in R, it's covered in the book, but you can always just do a question mark and then look at the function for the one you're interested in. So I'll do P binom, and let's compare that to the hypergeometric. So what's the probability that exactly 5 deer are tagged in my sample of 20. So what I'll do is I'll say, what's the probability using the binomial distribution where I have 5 successes, my size is 20, and my probability is 20%, or P. Oops, gotta run these. And so the probability of getting excuse me, that's 5 or fewer deer is 80%. Right. So, excuse me, I confused myself here. So D is the density, P is the cumulative distribution, and then R is to generate random ones. So if I want the probability of exactly 5, here we go. Okay, so the probability of getting exactly 5 would be about 17%, 17.45%. If I use the hypergeometric distribution, I believe it's hyper. Let me verify that before I type it. Yep. So we would say, again, we would say 5 size, instead of size here, it's, let's get these parameters right. So the number of white balls in the urn is M. So we had M equals 100. That'll be the tagged deer. The number of black balls in the urn is 400. So I guess I need to say the number of balls drawn from the urn is K equals 20. And X is 5. Sorry. Q is 5. And it's 0.808. So we look at this, and for binomial we got 0.804 for the cumulative probability. For hypergeometric we get 0.808. So very small difference. And again, I can do the density for exactly 5, and that's the one that needs X. And we get 17.77%. So the numbers are very close, which is why if you have less than 1/10 of the total sample size, you can get away with binomial. But if we had a much smaller sample, so let's say instead of 100 and 400, we had only 20, or let's say 40 and 2. Doing quick math, that's 160 then. These numbers change pretty dramatically. So the probabilities for binomial stay the same, right? 0.80 and 0.17. But when we do hypergeometric now, it starts to go up a little bit more, 0.815, so it's a little bit higher. The density, it's 0.183 instead of 0.177. And as we continue to make these numbers smaller, it'll change even more dramatically. Right? So if I switch it to 20 and 80, it goes up to 0.82. So you start to get more and more of a difference as you get closer and closer down to your sample size. So you got to be careful when you use binomial as a substitute for hypergeometric. So my reasoning there then is if we've got the computing power to do hypergeometric, don't use binomial for it. Use binomial only when it's appropriate. So unfortunately, when you read intro stats books, they use all these different approximation techniques because the people writing them are 80 years old and they learned it all before the computers could do what they can do. If we wanted to get a plot of the probability density, what we can do is we can do a bar plot of the probabilities. So if we're taking a sample of 20 deer, what we can do, I'll do the binomial one, we can do a bar plot of the binomial distribution density for X, which is 0 through 20 successes, and we'll say size equals 20, probability equals 0.2, And that's what the probability distribution looks like. And let me add one parameter here, just so we can get the labels down there. You can have anywhere from 0 to 20 successes, but with a probability of 20%, it's clustered at about 4 successes out of 20, and then it goes in each direction. It tails off, pretty close to a bell curve. But the probability of getting 13 or 15 successes is really, really low. It's really rare. So this is how you can get a plot of those densities. Let's take a look at geometric. So let's say we were going to go out and we've got the 500 deer, and we're going to go out and pick one until we find one that's tagged. So what we can do is say, let's do another plot of that distribution. So this will be dgeom for geometric. There is also a negative binomial distribution in here. And let me pull up the parameters. Okay, so we say x is the number of successes, so I want 1 success. Excuse me. I don't need to tell it how many successes, because successes is fixed at 1. So x is going to be the number of trials, number of failures. And so prob is still p. And if I plot that, what we see is that the probability that your first success occurs on the first trial is pretty high. It's about 20%. And that should make sense. We just said the probability of success on a single trial is 20%. So for the first trial, you got a 20% chance of success. The probability of success occurring on the second trial and not the first trial then drops quite a bit. It's down to 16%. And so as you go further, the probability that you make it this many trials without a success drops off considerably. All right, so this is the geometric distribution. It's an exponentially decreasing function. And if we go look at the formula for it, let me pull that back up. What we see here for geometric is that the probability is 1 minus p to the n minus 1 power. So there's that exponential factor times p, where n is the number of trials. Now R is set up, instead of saying number of trials, it's saying number of failures. So be careful about that. Here, what we're saying for 0 here is not 0 trials, right? The probability that you get your first success after 0 trials is 0, because it can't happen if you don't have any trials. So what the 0 through 20 represent down here is the number of failures that occur. So if you get your success on the first trial, that was 0 failures. So keep that in mind when you're working with R. It uses the number of failures rather than the number of trials. Negative binomial works very similarly. Except now you do need to tell it the number of successful trials. So if we wanted to say how many failures before we get 3 successes, what we would do is say x is our vector of the values that we're interested in, probability is p, and now we say size equals 3. And we get a slightly different distribution. And let me make a change here so we can see it go further out. Let's do x ranging from 0 to 40. And there, now we get almost like a Poisson distribution here, because the probability of getting all 3 successes immediately is pretty low. So it takes a few trials before we're likely to have reached our success level. But you can see here it's got this long right tail, which is why standard deviation is not a terribly useful measure here. Right? These are the equivalent of big outliers when you calculate the mean, and so they throw it off quite a bit. So I would encourage you to play with these different distributions, and the problems in the book give you a chance to do that. So let me pull up the module and we'll talk just a little bit about that. I have to log in again probably. Let me find it here. So if you look in module 3, the lesson walks you through the different families of discrete random variables. You've already studied binomial and geometric in the previous section, but this walks you through some other ones. And then I assign practice problems. So since it's the practice problem in the negative binomial section, you can guess that these problems require that distribution. So what I'll do is I'll also post a set of problems where you don't know the distribution and you have to try and figure it out. And I'll post answer keys to those as well. But I would start with these problems, work through these sections of the book, and then do the problems for those distributions. And that'll get you a good start. And then I'll post, well here, I'll just pull it up on the screen for now. I'm pulling the problems I've been using tonight from this sheet. I'll post all of these for you to look at. And then I've got some more also that I'll post. And again, I would use the discussion forum. You can refer to this. I'll give it a better title, and you can just say, from the supplemental problems number 3, I'm having trouble, blah, blah, blah. And I'll check that discussion forum a couple times every day, and you guys can answer each other. And just the more of these you work, the easier they are. Some of you may already have them down, and you don't need to work extras, but if you're struggling with identifying them, that's the best way to do it, is try one and then look up the answer and see if you got it right. Any questions at this point?
Yeah, just one. Is it possible for you to also post a reference sheet you're using too?
Which one? This one?
Yes.
I thought I had. Maybe I didn't post it. Yeah, I'll post it. I'll make sure it's there.
Okay.
I thought I had. I think I forgot. Thank you. Yeah, I will. What else? Any other questions? Watch as I post it this very minute. Quiet group tonight. I guess it's a small group too. Okay, so I'm going to post the problems and their answers and that review sheet. I'm on the verge of having posted them now. So if you have any other questions, let me know. Procedurally, are there any questions? The level of work's not too much. I'm still trying to figure that out. So you guys are able to get done what I'm giving you. I held off on this new module until you guys finished your group projects. I don't want to overwhelm you with stuff. So just so you can see in Module 3 now, the practice problems, the answer key, and that reference sheet are now here.
Thank you.
Mm-hmm.
Yeah, that's great.
And I think, unfortunately, it's possible the answer key's handwritten. So, so you'll have to... my handwriting's not too bad, I hope. You should be able to get the answers. And if you think there's one that's wrong, it is possible that there's one that's wrong. I'll go back and double check them, but if you find one you think I've got the wrong answer there, let me know. I would encourage you to try and do the answers in R, just because it's always good to practice the stuff in R. So learn how to use D binom, P binom, and do those calculations. When will you get the next collaborative assignment? Well, so let me go back to Blackboard here and just show this. The individual assignment here is due on Friday, October 10th. The next collaborative assignment will be due on, I'll probably say Monday, October 20th. But I'll post it a lot sooner. I won't post it after Friday, the 10th. I'll post it maybe Monday, this Monday. So you'll have lots of time to work on it. And it'll use the, it'll all be the discrete stuff still. The next one will still be discrete stuff. I haven't decided which problem I want to give you. I've got a few choices. I might even just give you 2 of them. So, any other questions? It looked like the 2 groups worked pretty well together, so I don't think there's any need to change it up at all. Let me know privately if you think otherwise, but it looks like the 2 groups did. I mean, you both turned in fantastic projects, so I That's what it's all about.
Thank you.
All right, yep, thanks. So 2 weeks, and again, I do have office hours on Tuesdays. I don't think I'll miss any more of those this term unless I'm ill. Last time I was supposed to be in Kansas, so I was going to miss it because of that, and then I ended up ill, so I still couldn't hold it. But if you have any questions, you've got the Ask Your Instructor forum, and then email me. We can always set up a quick meeting and meet one-on-one other times. I'm an independent contractor, so I've got a pretty flexible schedule, so you got to let me know. Okay, if that's it, then I'm going to end the session, and I'll see you in 2 weeks.